Hello, everyone. Thank you for joining today's webinar. My name is Dan Blainer. I'm a solutions architect specializing in Amazon's Quantum Ledger Database, otherwise known as QLDB. With me today is Matt Lewis, Chief Architect for the UK's Driver and Vehicle Licensing Agency. Matt is going to provide you with the DVLA's perspective on building an event-triggered system of record application with QLDB. Before I hand things off to Matt, I'll give a brief overview of QLDB. Following Matt's presentation, we'll take some Q&A. QLDB is a fully managed ledger database that provides an immutable and cryptographically verifiable transaction log, giving customers a transparent history of all transactions against the ledger. Transactions are appended to the journal in blocks instead of overwriting data stored on disk. QLDB creates cryptographic hashes of transactions to prove the integrity of the journal. In QLDB, your data is stored across multiple locations in multiple availability zones, making it highly durable and available. QLDB manages scaling on your behalf. Simply create a ledger using the console, command line interface, or SDKs, and QLDB manages the rest. No service to worry about. QLDB is easy to use. Interacting with QLDB is a lot like interacting with other managed NoSQL databases. Data is stored in a JSON-like format called Amazon Ion and queried with a SQL dialect called Particle. Both Ion and Particle have been open sourced. QLDB supports ACID transactions at the highest isolation level. Serializable, giving the best concurrency protection without performance penalty. QLDB is the latest purpose-built database offered by AWS. Instead of using relational databases for everything, our customers demand the ability to use a database engine that is optimized for their application's needs. As you can see from this slide, we offer a broad category of databases with deep features in each category. At reInvent in December, we announced the private preview of QLDB Streaming. QLDB Streams capture all document revisions committed to your journal and delivers them in near real time to Amazon Kinesis data streams. Customers can consume data from the stream to drive event-based logic for real-time analytics and to feed data from your journal into data warehouses, relational databases, Elasticsearch, and other purpose-built databases. QLDB is in private preview now and will be generally available very soon. With that, I will hand it over to Matt Lewis from DVLA. Matt?
Thanks, Dan. So my name is Matt Lewis, and I'm Chief Architect at the Driver and Vehicle Licensing Agency in the UK. So we have a number of core responsibilities, and these include the registration and licensing of all drivers in Great Britain, which includes issuing out photocard driving licenses, the registration and licensing of all vehicles in the UK, which includes issuing all vehicle registration certificates, and collecting vehicle excise duty. So this all links to our goal of getting the right drivers and vehicles taxed and on the road as simply, safely, and efficiently as possible. Now, at the heart of the agency are a number of systems of record. We operate as the centralized trusted authority for these canonical registers, and we are responsible for ensuring the integrity and the accuracy of the data contained within them. There are 5 main systems of record that we maintain. Trailers that are authorized to travel across Europe, tachograph cards, the most common being driver cards that are fitted into commercial vehicles like trucks and coaches, and they record information about driving time, speed, distance, and rest periods to improve road safety. Vehicle registration numbers or license plates, as every vehicle in the UK must have a unique license plate. And then we have our 2 core registers, which are considered part of the UK's critical national infrastructure, and these are vehicles and drivers. We have around 43.5 million active vehicle records, and they contain details about the vehicle, the history of registered keepers associated with them, and their license status. So every vehicle needs to be licensed each year to be driven on public roads. Last year, we processed over 50 million licensing transactions and collected around £6 billion in vehicle excise duty. We also hold 49.5 million active driver records. Now, this contains personal information such as names and addresses and driving license numbers, as well as entitlements, which are the categories of vehicle a person's eligible to drive, and endorsements, which are penalty points on your license, as well as medical restrictions and biometric data such as photographs and signatures. So overall, we interact with over 92% of the entire adult population in the UK and virtually every single household. And what we're increasingly seeing is the growing importance of data, the accuracy of that data, and the trust that sits behind it. If we go back just 5 years, there was a physical paper counterpart to your driving license in the UK. The paper counterpart held details about the types of vehicles you could drive and any penalty points on your license. If you received points, you needed to post the counterpart off to get them added, and then it was returned back to you in the post. In June 2015, the paper counterpart was officially abolished. So today, you view your driving license details online, you can generate a check code to share this information with someone else, like an employer or a car hire company online, and you can even add this check code to the wallet on your mobile phone. And this data is needed 24/7. It's a similar story on the vehicle side. Historically, you would determine if a vehicle was licensed or not by looking at a paper tax disc in the windscreen, and it was actually a legal requirement to display this disc. The paper tax disc was abolished in 2014, and now all interaction is against the electronic record. And this leaves us facing a number of business challenges. The first of these is the growing demand for our data. There are government initiatives to support enforcement functions, which are linked to identification and verification. There are also environmental initiatives like clean air zones, alongside parking permits, car sharing schemes, and the volumes for inquiries are increasing exponentially. And at the same time, we see a growing demand for our data. The data itself is evolving. If we take the vehicle side, the attributes associated with the vehicle change as we move towards electric and autonomous vehicles. Our vehicle's system of record is many years old and is built on traditional relational database technology. It has a rigid database schema defined a long time ago, and adding new attributes is an invasive operation. And all the time, the data provenance or data lineage remains critical. This is the ability to go back and prove what the state of a record was at any point in time and what caused that change. This is vital as our data is used for enforcement and for prosecution. It's used when you apply for insurance or whenever you pick up a rental car. We need to be able to prove who the registered keeper of a vehicle was, whether that vehicle was licensed, whether the driver had the correct entitlements to drive that vehicle, and the state of their license at any given point in time. So what are some of the challenges of the traditional approach? At a simplistic level, in a traditional approach, users interact with an application through various channels, whether paper, web, API, and the application updates the system of record supported by DBAs. The application may also create an audit trail. And this is the case where we have systems of record over 10 years old that run in our own Crown commercial data centers. And there are a number of pain points with this. So let's start with a relational database. From the outset, they are not designed to be immutable. For example, if you launch an RDS instance today, you're created with a super user role. And this has administrative privileges and tasks which allow you to set fine-grained controls and change default privileges. We also require resources to operate some of our databases, and that's including installing, patching, supporting, and general maintenance, although that does change with more modern managed database services. We also have a rigid defined schema that has evolved over many years, and as stated earlier, it causes difficulty when we need to change it. And there are also issues around scalability. This is a common challenge aimed at relational databases, especially when we have a growing data set and you have complexity around SQL joins, as well as horizontal scaling issues, especially when there's no clear way to split up or shard the data to ensure that single requests are handled by a single server. Audit trails themselves are typically written as part of the application, and this requires custom development to take place. This means that with an evolving data set, and as new attributes are added to the system of record, custom development is required to change the capture of this audit information. In addition, there are invariably going to be legitimate business scenarios that are so rare, the functionality to handle it isn't built into the application. In this case, a typical outcome is that the data will be updated directly through a version-controlled script. However, this has the result of them bypassing the audit trail. So how might a future state architecture look using QLDB. At DVLA, because of the data that we hold, we naturally need to handle orders of magnitude more reads than writes. Because of that, we advocate a pattern called Command Query Responsibility Segregation, or CQRS. This is a way of separating out reads from writes. A command is any method that mutates state, and a query is any method that returns a value. So QLDB can sit as the source of truth for a system of record, and we can interact with it with our application via a command that could be synchronous or asynchronous, but then data can be streamed out into the most appropriate read model for inquiries. But what are the features that attracted us to look at QLDB? When we talk about QLDB, there are a number of features that provide distinct advantages. So let's drill down into some of them. We start off with journal-first architecture. So many modern database systems use an internal transaction log or journal. So Postgres and MongoDB use write-ahead logs, Oracle has redo logs. And the approach here is broadly similar in that all changes are written first to journal files before being written to the data files where the tables of the data reside. And this means in the event of a system failure, the database can be recovered and brought back to a consistent state by applying changes from the journal. However, in these implementations, the transaction log or the journal is hidden away from the developer. QLDB adopts a journal-first architecture where the journal is treated as a first-class citizen, it's externalized, and it's append-only and immutable. No record can be updated without going through the journal first. The journal itself only contains committed transactions, and so it's not concerned with handling rollbacks. All interaction with QLDB takes place within a transaction with full serializable isolation. This is the strictest level of isolation. In technical terms, QLDB uses optimistic concurrency control. What this means is that when the application attempts to commit the transaction, all of the state, which includes all the reads and the writes, is submitted to the journal. QLDB then checks to see if another transaction has interfered or modified with the data being accessed, and in which case it will reject the transaction back to the calling application when that happens. So this is why QLDB is able to offer such strong guarantees around the completeness of the data. As a transaction is committed to the journal, a cryptographic digest, SHA-256, is computed and stored as part of the transaction in a block. This is a one-way hash function that produces a unique fixed-length signature. There is no way to reverse that signature and reproduce the original document just from that hash. QLDB uses hash chaining, and that means each time a new block is added, the hash for that block is combined with the previous chained block. So as the journal acts as an immutable append-only log, QLDB makes it easy to interact with using Particle, which is the SQL-compatible language familiar to most engineers. When a transaction is committed to the journal, QLDB automatically creates a queryable view of the data, and this gets materialized in real time and is eventually consistent. The user view itself only contains the latest revision of data, but there's also a history function in Particle that allows the entire revision history of data for a record or document to be viewed. AWS allow you to export the whole ledger for a specified date and time range into S3. This can be carried out for audit, analytics, backup, or a variety of other different purposes. And all of the blocks of data in the journal are exported. And what you notice from the sample output shown here is that the particle commands that are executed against the ledger form part of the block. So that gives you the ability to export and check all commands that have been executed and successfully committed. As well as hash chaining, QLDB builds a continuously updating Merkle tree on top of the journal. At any point in time, you can request a digest for a given ledger. This represents the root of the Merkle tree and can be used to verify the data integrity of a record to show that it's not been tampered with. So to try and bring this to life, we built a demo bicycle license application. This helps to give an overview of the basic workings of QLDB, covering the journal, the current state and indexed history, and cryptographic verification. Let's start with the first demo showing some basic functionality of QLDB. At the moment, we're here in the QLDB console, and you can see that we have a ledger called Bicycle License Ledger with a table called License. So I can carry out some basic queries against the table, and these are carried out to show that it's empty, so there are 0 records returned. And at the moment, I'm interacting with the ledger using Particle, which is the SQL compatible language. Now, let's go and create a record using our new Bicycle License application. We start off by creating a new record by entering some basic details. Once we've entered these details, we add the record. Now we can see from the message that a new license has been added. It has a guaranteed unique system identifier, which is the ID generated by QLDB, which can be found in the metadata section. We can now go back into the console, and here we can query the user view to show the latest application data. And now by selecting the record, you can view it as an Amazon Iron document. You can also query the committed view. This is the view that contains the QLDB generated metadata. So you can query this view by adding _QL_committed_ to the table name. So when we run that query, this is then the Amazon Iron document that gets returned. This returned document contains the block address. This shows the location of the block in the journal where it was committed. The block address contains a strand ID, which is the unique ID of the journal strand. QLDB currently supports journals with a single strand only, so you'll see this value is the same for all blocks. And then the sequence number is the location of this specific block in the strand. The next value is the hash. This is the SHA-256 value for this block that's generated when the transaction is committed to the journal. It is generated using the data and metadata fields, and it's this hash that enables cryptographic verification. The data section contains the data written to the table by our application, so this is our user data. And the metadata is the system-generated data. This contains the ID, which is the unique identifier of the document. It contains a version number. This is a 0-based integer, so the first time a document is created it's 0, and each time it's updated, this number is incremented. Finally, it also contains the timestamp where the transaction was committed, and the unique ID of the transaction. Now, let's go back and make some updates to this record. In our application, we can search in the ledger for a record, and when we find it, we can then update the record, in this case adding penalty points. If we want to, we can search again for the record and then make another change, this time by updating the telephone number. Now, when we go back into the QLDB console and query on that record, we can see that the document that gets returned has the current state only. But what we are interested in is the full audit history of all changes to this record over time. So let's go back into our application and into the History tab. In the History tab of our demo application, we make use of the History function in QLDB. This is a really powerful feature that allows you to search for all revisions of a document held in the ledger. Now, when we search for this particular document, it shows that there are 3 revisions. For our demo application, we've broken this down into information around the metadata, integrity, and the application data, which we've called document. If we click on the very first document, we can see the first version that was created. The next revision shows the first update. We also add the reason for the update into the document, so we can see that the document was changed because penalty points were added. The final revision shows that the telephone number has been changed. We can also now expand the metadata section for all revisions. In the metadata, we can see the unique ID of the document, which is the same across all revisions. We can also see how the version number has been incremented for every single revision. This is hugely important. It means that you cannot simply overwrite a record. With QLDB in the history function, you can go back and look at what the state of a record was at any point in time. But what makes QLDB stand out is not just the fact that you have the complete audit trail of every single change made, but that you can also verify the integrity of that data. In the integrity section, we show the information about the block address for the specific document revision, which we saw earlier in the committed view. The first step in the verification process is to request a digest from the ledger. The digest is a cryptographic representation of the ledger's entire journal at that point in time. You can see what a digest looks like by using the getDigest command on the CLI. The output file contains the tip address, which is the location of the latest committed block in the journal, and the SHA-256 hash of the digest. To verify the integrity of the specific document revision, we can call a QLDB control plane API such as getRevision, passing in the block address of the document revision to be verified, the digest tip address, and the unique document ID. This returns a proof. You can then use this proof to recalculate the digest, starting with your revision hash. If the hash that you recalculate matches the digest hash, then cryptographic verification has been successful. This means we know that this specific document revision is in the same location in the journal and has not been altered in any way. So this demo has run through a number of basic operations in QLDB. It's shown how each document is immutable and how in updating the record you're creating a new document revision. The history function allows you to view all revisions for a given document, and using the digest, you're able to cryptographically verify each record.
So these core features of QLDB are great, but we still have challenges that we need to address. In order to handle high volume inquiries, we need to provide read models that only contain the data necessary in a denormalized format that can be returned quickly. We're also looking at an event-driven approach where we can build decoupled services that react to events that take place around them. So this uses choreography and not orchestration, and they can scale up and scale down independently. The answer to this has come with the announcement of Streams. So please note, this is currently in private preview, so some of the features may change. QLDB Streams supports a change data capture pattern, where all changes are streamed out to a Kinesis data stream, and this offers many advantages. All committed changes from the journal are streamed out. QLDB remains the source of truth, but it enables downstream systems or components to take the appropriate action. This could be used to support data analytics. It could be used to support event-driven processing. So in our bicycle license application, we could emit an event that has an action around bicycle license created, and a downstream component could use this to print and dispatch a new license. It can also be used to populate a purpose-built database. Kinesis provides an at least once delivery guarantee, and multiple streams can be set up with different start and end dates and times. It also increases the security posture. Read models can be set up and configured to contain only data that is necessary, and so we can enforce least privilege. But let's see this in action.
In our application, we've exposed a license activity inquiry. This allows you to look up the current number of penalty points held against a license and show all the activity that's taken place. For demonstration purposes, we filter out certain attributes such as the full name, telephone number, and email address. This is to show how you can create new read models using purpose-built databases that contain only the data needed. For this example, we're using DynamoDB. This allows us to expose a single-digit millisecond latency inquiry keyed by document ID. So, to start off, we go and retrieve the document ID from the metadata. Then, we go to the License Activity tab and carry out a search. Unfortunately, no data is available at this time. If we go across into the DynamoDB table and query, we'll see that no records are found. So what we need to do is create a new QLDB stream specifying the ledger to be used. Note that you can specify a start date and time and an optional end date and time for streaming journal data. We put the start date back a few days to make sure we pick up all document revisions committed to the journal, and not just the ones from this point. Then we specify a Kinesis data stream as a target resource to which this QLDB stream will write all the data record. We then specify an IAM role that has the correct permissions to allow QLDB to write to the Kinesis data stream. We then create the QLDB stream. And straight away, this begins streaming blocks from the ledger to Kinesis. We have a Lambda function that has the Kinesis data stream as an event trigger. When we refresh CloudWatch, we see that data is already being picked up and processed by the function. QLDB writes 3 different types of data record to Kinesis: a control record that indicates the start and completion of the QLDB stream, a block summary record that represents a journal block in which your document revisions are committed, and a revision details record that represents the document revision committed to the ledger. Now when we go back into Dynamo and refresh, our record appears. Note that we have just one individual record in Dynamo, and that this has been updated after each individual document revision. When we go back into our Bicycle license application and search again, we've successfully retrieved the record. We did this by connecting a QLDB stream up to a Kinesis data stream that triggered a Lambda function that wrote to DynamoDB. At no point did we have to provision or manage any underlying infrastructure. That has all been taken care of for us by AWS. Let's go into QLDB now and delete the record from the table in the ledger, just to see what happens. So we execute the query and we can see that that document ID has been affected. Now, when we try and run a select, we can see that no rows have been affected, so the record has now been deleted from the current view. Back in our Bicycle license application, when we look up this record, we can see that that license no longer exists. We can also go and check in the license activity. And again, when we search, it comes back with the error message that the data is unavailable in DynamoDB. If we refresh the data in Dynamo, we can see that that record has now been deleted. So we've seen that deleting a record in the table using the delete statement of particle has been committed to the journal. That change has been reflected in the user tables, so it can no longer be found, and that change has also been streamed out to QLDB, causing the record in Dynamo to be deleted as well. But if QLDB is immutable, what has happened to that document? If we go back into our application, we can search using the history function by passing in the unique ID of the document held in the system-generated metadata. When we search using the document ID, we can see that all revisions of that document are returned. If we open up the latest revision, all the data has been deleted. In reality, the block that gets committed to the journal has no data section, but we've interpreted that here to explicitly show that means the record has been deleted. This is incredibly powerful functionality. Even though a record may have been deleted, and it can no longer be found when queried with the user view or committed view that is created for you in QLDB, or can no longer be found in any downstream purpose-built database, it will still remain in the journal. For us, this is a compelling use case where the journal always remains as the source of truth. The document revisions are immutable, they are complete, and they can be cryptographically verified.
In terms of next steps, I'd love to hear more about how people are using QLDB. So please get in touch via my Twitter handle. I'm also in the process of curating content such as guides, developer tools, and resources for QLDB. And this can be found in the awesome QLDB repository. At the same time, I'm putting together a QLDB guide that will provide some best practices and findings from building out these sample applications. So please get in touch, collaborate, and help grow this community. With this, I'll hand back to Dan.
Okay, thanks, Matt. And thank you everyone else for joining our webinar. With that, we'll take some Q&A.